Hello everyone, and welcome to this short presentation called Towards Naturalistic Speech Decoding from Brain Data. Speech decoding from brain activity can enable development of brain-computer interfaces to restore communication in paralyzed patients. Relative success in neural decoding of continuous speech signals has already been demonstrated using deep artificial neural networks. This initial work is promising, yet good performance is typically observed in isolated speech, as in words and sentences with a clean background, with multiple repetitions of the material. More robust brain decoding that can tackle noisy, naturalistic environments and produce high-quality natural speech reconstructions remains needed. In the field of vision, recent work has shown promise of generative adversarial neural networks, or GANs, in photorealistic reconstruction of images from brain activity. Instead of decoding complex, high-dimensional data such as natural images directly from the brain, pre-trained GANs are used to generate this output from a compressed latent vector of only 100 to 300 values. This latent vector is decoded from the brain activity. In this study, we rely on this previous promising work from vision as inspiration for building a GAN-based speech decoder and evaluate it against other methods. In this study, we used an intracranial EEG dataset in which 11 patients with electrode grids and 8 patients with depth electrodes watched the full-length feature film in their native language, which was Dutch. We extracted high gamma traces from the data and used them as input to neural decoders. Our speech GAN model was based on the spec-GAN architecture. The GAN model was trained on 5.5 hours of Dutch speech. We trained 3 neural decoders. First, the vanilla decoder was trained to predict audio spectrograms directly from the brain input by passing it through a set of convolutional layers with skip connections. Second, the GAN-D decoder had the same architecture as vanilla, but was trained using an additional feature loss. Speech GAN's discriminator was used as a feature extractor for computing this loss. Third, the GAN-based neural decoder, termed GAN-Z, was trained on brain input to predict latent vectors that were then input to the generator of the speech GAN to produce the audio spectrograms. The GAN-Z decoder also minimized the additional feature loss during training. We used another pre-trained neural network called parallel waveGAN to synthesize speech waveforms from reconstructed spectrograms. First, we confirmed that after training, the speech GAN model was able to generate high-quality naturalistic speech. We found that several randomly generated fragments contained intelligible speech, and many sounded like speech, yet were not intelligible.
Wel bij de decoding is multiple sheet. Is niet
Quantitatively, the difference between generated and real speech fragments was similar to the difference between the real speech fragments and real speech fragments resynthesized from spectrogram with parallel waveGAN. Second, we compared sound reconstructions obtained with vanilla, GAN-D, and GAN-Z neural decoders. We found that models that were directly trained to predict spectrogram values, such as vanilla and GAN-D, reconstructed low-level features of spectrograms better compared to GAN-Z. On the other hand, the GAN-Z model detected speech boundaries and reconstructed pitch more accurately compared to the other models. From visual inspection of spectrograms, it was clear that the GAN-Z model better captured the high-level structure of speech, including formants. This became even more apparent when we listened to sound reconstructions. Only the GAN-Z decoder produced natural-sounding speech.
Noes. Ik had hem even verkeerd. Noes. Ik had hem even verkeerd. Maar later gaan we maar snel. Noes. Service. Ik had hem even verkeerd. Even kijken. Zo. Maar later gaan we maar snel. Hou je goed bij daar.
Finally, we made an attempt to explore the latent space and relate high-level sound properties of that space to the brain input. We were able to identify subspaces of the latent space that corresponded to generation of voiced and unvoiced sounds. This allowed us to construct a voice gradient with high scores for continuous speech fragments and low scores for fragments without speech. The brain activity map that corresponded to the voice part of the gradient contained electrodes in the temporal cortex with peaking values in the Hatchell's gyrus. The results of this study once again highlight that naturalistic speech decoding is a difficult task, especially when noisy naturalistic data are used as opposed to individual isolated words and sentences with repetitions. However, we found that in this noisy setting, GAN-based models are best suited to pick up high-level speech features, which leads to better decoding of pitch and form and structure, and as a result, reconstruction of more natural-sounding speech compared to other approaches. This makes GAN-based models a good candidate for future BCI speech decoding applications.